It's my great pleasure to present Professor Dan Segal from University of Oxford. He'll talk about rings, groups, and logic. So.
Okay, thank you, Shayla. Thank you very much for inviting me to talk in Brasilia. I've never done this before. I don't know if I ever will, but this is the closest we can get to it. Anyway, as I was saying to some of you, hello, Christina, I've just seen you. Sorry, I'll stop doing this. I've not done one of these before, so I was a bit nervous. And what I would really like is, please do feel free to interrupt me and ask questions whenever you feel like it, because that will make it seem a bit more human and less detached. So I've prepared these slides anyway, so I'll talk and I'll go through the slides as we go along. So as those of you who know me know, I'm not really a logician at all. So I only got, what I'm interested in is groups and algebra and number theory. But I met some logicians a couple of years ago and they asked me a question and I thought, oh, well, maybe I could do that. So this resulted in a certain amount of work we did together. So I shall start talking about it now. So the idea is, everyone knows about first order logic. You can have the language of groups or the language of rings or whatever. So you have the symbols for the operations of your structure, and then you're allowed first order logical symbols and quantifiers, and that's it. And as we all know, you can't say very much of interest about infinite structures just using first order logic, because you can't really talk about subsets. You can only talk about elements and relations between them. So the vague sort of background question is, how much can you say about a group just using first order language? For example, can you determine a group just by its first order properties? If you can, the group is said to be axiomatizable or first order rigid. Or even more strongly, you might ask, which groups have the property that you can actually determine the group up to isomorphism just by a single sentence? And you might think, well, this doesn't often happen. And in a sense, it never happens unless the group is finite, because the Löwenheim-Skolem theorem says that any system which has an infinite model has infinite models of lots of different cardinalities. So you can't pin it down up to isomorphism unless you say something else. But if you restrict the class of structures, groups, for example, that you're talking about, then of course it makes sense. For example, you can talk about a group being finitely axiomatizable. A group is finitely axiomatizable in a class C if there's a sentence sigma of the first order language of group theory such that G satisfies sigma, and the only groups in C which satisfy sigma are those which are isomorphic to G. So the sentence determines the group up to isomorphism within a certain class. And quite a lot of papers were written about the particular case of the class of finitely generated groups. Andre Nies introduced this term, quasi-finitely axiomatizable, QFA, equal the group G quasi QFA if there is a single sentence of first order group theory which says that for all finitely generated groups, it determines that group within them. So Nies wrote several papers and produced also a certain number of examples, not very many, but different kinds of examples of finitely axiomatizable groups. And there's a nice paper by Auger and Sabat which actually gives a characterization of those finitely generated nilpotent groups that have this property. And I won't say what it is because I'm going to generalize it in a minute. Okay, so what Andre Nies asked me actually was, which profinite groups are finitely axiomatizable among profinite groups? Because he knows that I know about profinite groups. They're not much about logic. So I thought, okay, let's look at this. And there's a bit of background here. Usually it's difficult to talk about subgroups in first order logic because you need to talk about products of arbitrarily many elements, if you want the subgroup generated by a set X. So if X is a definable set, for example, a finite set, the subgroup generated by X is not usually definable because to be in that subgroup, means to be a product of a certain number of elements of X or their inverses, but a priori you don't know how many elements. And if you're in the profinite world, of course, then you can talk about the closed subgroup generated by X, and it's even more difficult to talk about that using first order language. However, if you just consider products of a bounded number of elements, then of course that is definable. It's easy to write down a sentence which says that some element is equal to a product of n elements from your definable set. And as most of you know, in a profinite group, if X was a finite subset, then the subgroup generated by X is closed if and only if every element of that subgroup is a product of a bounded number of elements. Actually, this isn't quite correct, is it? You have to allow inverses. Let's assume, just for this bit of the discussion, that the set X contains the inverses of all its elements. Okay, so if a subgroup has finite width with respect to a certain generating set, then it's definable in first order language within profinite groups. Okay, so there's a theorem that Nikolai and I proved a few years ago, which gives an example of lots of definable subgroups in that sense. If a profinite group is finitely generated as a profinite group, then you let X to be the set of all mth powers. Not a finite set, but it's a definable set, obviously. Then every product of mth powers is actually a product of boundedly many mth powers. So that means that the subgroup generated by the mth powers, g to the m, is a closed subgroup. And more to the point, it's definable because of this bound. Okay, so now in particular, it means that every finite quotient of the group is, of course, if you have a subgroup of finite index, it contains the subgroup generated by mth powers for some m. And it's easy to see that the subgroup is then definable in the group. And once you can define the subgroups of finite index, you can then describe the structure of the finite quotients in a fairly straightforward way. So every finite quotient of the group can be described in the first order language of group theory. And this, once you've realized that, you then can see that actually, because a profinite group is determined by its finite quotients, Lubotsky and Yarden observed that using what I just talked about before, the group will actually be determined up to isomorphism by its first order theory, the set of all first order sentences it satisfies. It's what Lubotsky calls first order rigid. Okay, so this is not the main topic I'm going to talk about, but this is kind of the background where first order logic and profinite groups sort of interact. So to say it's first order rigid means the group is determined by an infinite family of sentences, all the sentences which are true about the group. Is it finitely axiomatizable? Can there be just one sentence? And the answer is usually not. And this goes back to Wanda Chmielew, who's a Polish mathematician back in the 1950s, I think, who did this for abelian groups. And then Auger and Sabat generalized it to groups which are not necessarily abelian, but which have quite a lot of center. So this theorem, as formulated by Auger and Sabat, says if G is a group such that the center modulo the derived group, I mean the center of the group times the derived group modulo the derived group, is not periodic, then any sentence satisfied by G will also be satisfied by the direct product of G with a cyclic group of prime order for almost all primes P. So in particular, if the group is finitely generated, or if it's finitely generated as a profinite group, it obviously can't be determined by a single sentence, because it would then have to be isomorphic to its own direct product with a cyclic group of prime order, which is not the case. So for example, the group Z hat, the free procyclic group, is not finitely axiomatizable among profinite groups, because any sentence satisfied by that group will be satisfied by the same group direct product cyclic group of prime order for most primes P. Okay, so the question is, are the conditions which do say that a profinite group is going to be finitely axiomatizable? And the answer is yes. Before I go on to that, I'll say, for the same reason that Z hat is not finitely axiomatizable, you can say that being generated by a given number of elements can't be determined by a first order sentence for the same sort of reason. Okay. However, the interesting thing about P groups is that you can tell how many generators a P group needs by looking at a very small finite quotient. You look at G over G to the P. And if you have a pro or a pro P group for the same reason, okay. So a pro P group G can be generated by D elements if and only if you factor out its Frattini, the quotient by the Frattini subgroup has at most a size at most P to the D. And that's, turns out you can express as a first order statement, even if you didn't know to begin with that the group was finitely generated. Okay. And I thought about this a bit and I realized that you could say the same thing about groups having finite rank. So a profinite group has a rank R, or at most R. It's what used to be called the proof rank, if every closed subgroup can be generated by at most R elements, topologically. Okay, and this is also a first order property, it turns out, for pro P groups. So if you assume a group is a pro P group, then it satisfies this sentence R. Well, I don't know if you can actually pin down the rank by a first order sentence. So that's, if you like, an exercise for the audience. But I certainly, there's a sentence which says that it implies that the rank is at most some bounded function of R. And conversely, if it has finite rank R, then it satisfies some such sentence. Okay, so having bounded rank for a pro P group is more or less expressible as a first order property. Okay, and these pro P groups are particularly nice, and they're what's called p-adic analytic pro P groups. And when Andre Nies asked me about finite axiomatizability, I thought it shouldn't be too difficult to do it for p-adic analytic pro P groups, because basically because of this property that we can control their rank and we can control the numbers of generators and so on. And indeed, this worked out quite well. So in joint work with Andre Nies and Catherine Tent, which is in a paper on Archive, if you wanted to read more details, we prove, for example, two theorems. The first theorem is that if you have a p-adic analytic pro P group G, and you ask, is it finitely axiomatizable among p-adic analytic pro P groups? In other words, you're limiting the universe to this very special class of groups. Then the answer is yes, provided you've got is sufficiently finitely presented. So if the group has a finite presentation as a pro P group in which the relators are just ordinary group words, not profinite words, then that's a sufficient condition. Or you don't need any condition about presentation, but you have to extend your first order language to allow p-adic powers. So it becomes the first order language of pro P group theory rather than group theory. So that's the theorem about p-adic analytic groups. And now we generalized the theorem of Auger and Sabat, who characterized finitely generated nilpotent groups among abstract groups that are finitely axiomatizable by proving essentially the same theorem for pro P groups. Okay, a finitely generated nilpotent pro P group is finitely axiomatizable among all profinite groups, not just pro P groups, if and only if its center doesn't stick out too far above the derived group. That condition, which I showed earlier, was necessary for a group to be finitely axiomatizable. Okay, again, we have to assume one of these conditions, A or B. And the reason we have to assume them is kind of fairly obvious once you think about it, because if you don't assume something like that, you get uncountably many different groups. It's easy to see there are uncountably many, for example, finitely generated nilpotent pro P groups with whose center is contained in the derived group, for example, so they satisfy this condition. But there are only countably many sentences in the language of group theory. So either you have to allow p-adic powers So you get uncountably many sentences, or you have to restrict to groups which are finitely presented in the rather strong sense of group theory. Okay, so that's what we did about pro-p groups. Similarly, instead, you can move from pro-p groups to products of finitely many pro-p groups with different primes. But you can't do the same thing for infinitely many primes, because basically, well, I won't explain why, but basically, as soon as you allow infinitely many primes, the groups stop being finitely describable in first order language. But I don't want to go into that because I want to talk about other things. Okay, so combining the two theorems I mentioned before, these two, we can deal with all sorts of interesting groups, you see, because these are nilpotent groups. You might say they're rather special, but these are all p-adic analytic groups. So if you have a p-adic analytic group, which might not be nilpotent, but you can prove it's a pro-p group, or rather you can express the fact that it's a pro-p group in first order language, then once you know it's a pro-p group, you can then use the first theorem to say, okay, there's a sentence which characterizes this group among pro-p groups, and therefore the group itself can be characterized by a single sentence among all profinite groups. And for example, we prove that groups like SLDZP have this property. They are finitely axiomatizable. And the kind of arguments are all group theoretic. We don't use any logic for this sort of stuff. And basically it uses the fact that these p-adic analytic groups have a dimension. So you can describe a finite group sort of easily because it only has finitely many elements. And in a sense, you can describe a p-adic analytic group quite easily because it has finite dimension. So I won't try and explain this more than that, but that's basically why this kind of machinery one uses for these sort of things. Okay, so that's the first part of the talk, some results about profinite groups, specifically pro-p groups.
Dan, may I ask you?
Yes.
Here, as I understand, any analytic pro-p group has dimensions. So you don't talk about dimension of analytic pro-p group here.
These are I do, yes.
So why for this group you can use dimension, and for any other analytic pro-p group you cannot?
Sorry, what do you mean? Oh, you can. I mean, you can use it for all p-adic. We use the dimension to prove this theorem.
Ah, right. Okay.
Yeah. Okay. I mean, basically, because you have these groups have always finitely presented as pro-p groups.
Yeah.
So you might have p-adic powers. Okay. Yeah. So once you have the finite presentation, you then can express quite easily the fact that another group is an epimorphic image of this group. Okay. And now we use the dimension to determine whether this epimorphism is an isomorphism. Mm-hmm. That's the basic idea.
Thanks.
Okay. Right. So this is, I'll come back to some more questions about profinite groups maybe at the end, but I wanted to get away from profinite groups because we've actually spread our wings in a different direction. So this is the next bit, a different approach. I mentioned rings in the title, and whereas these p-adic analytic groups, I mean, they have the p-adic integers sort of sitting inside them, but the group might be quite complicated and not easily definable in terms of the integers, unless it's something like SLDZP, where it's actually a group scheme, a functor from rings to groups. So we can pick up this idea and consider other group functors and other rings. So what I've written here is we can express group theoretic properties of the group as ring theoretic properties of the ring. I mean, it's clear that any equation among matrices can be written as a lot of equations using polynomial equations among ring elements. So first order group theoretic properties of SLDZP, for example, can be expressed as ring theoretic properties of the ring ZP. So if the ring happens to be finitely axiomatizable, or first order rigid, or has some other first order property, then you can translate that into analogous properties for the group. And these kind of things can be easier for rings than they are for groups. For example, it's quite easy to establish that the p-adic integers is finitely axiomatizable among profinite rings. You could do that in your head while I'm talking, if you like. You know, once you fix the prime p, you say it has a unique maximal ideal, which consists of p products, which are multiples of p, and all the rest of it. Okay, so we need a way of translating from groups to rings and back again. And the model theorists have something called bi-interpretation, which says you have one structure and another structure, and they're bi-interpretable. If anything you can say about the one structure in the first order language of that structure translates into something you can say about the other structure in the first order language of the other structure. So I'll move on to that, giving a slightly more formal definition, but specifically about groups and rings. So you have a group gamma and a ring R, and we'll say they are bi-interpretable. This is a equivalence relation. If gamma is interpretable in R, and R is interpretable in gamma, and the resulting map from gamma to itself, I shall be a bit more precise in a minute, is definable. So to say that gamma is interpretable in R means that you have some finite power of R and a definable subset of this, which is identifiable with the group gamma. And the group operation in gamma can be defined using the first order language of the ring. So I'll give you an example in a minute. Similarly, you have the ring can be identified with some definable subset of some power of the group, some finite power of the group. And the ring operations must be definable using the language of group theory among these M tuples of the group. And the map from the so you can embed the group as n tuples of the ring. Each ring element can then be expressed as an M tuple in the group. So you're combining these maps, you get a map from the group into some mnth power of the group. Okay, and the way it's been set up, this map is automatically an isomorphism. And the important thing is that this isomorphism should be definable just using the language of the group gamma, without mentioning the ring in the middle. So if you're not familiar with this, it will become clearer in a minute. And I haven't mentioned it, but there's another condition to make it symmetric. In other words, the map from the ring from R into R to the NM is also definable in the language of rings. But as we'll see in a minute, this is not such a difficult condition to satisfy. Anyway, the point is that once you've got this, it's then quite easy to see that any first order property of the ring of the group can be translated to a first order property of the ring, and vice versa. And in particular, if the ring is finitely axiomatizable or axiomatizable in a certain class of rings, then the group will be axiomatizable in a similar way in a corresponding class of groups. So let's look at the example of SLDR gamma. So, of course, gamma actually either is identified or is equal to, depending how you like to define it, a set of matrices over the ring. So you could think of them as d squared tuples. And to multiply two matrices, you just use ring operations on the entries. So the group operation is definable using ring language. To identify the ring inside the group, you take, for example, triangular matrices with just non-zero entry in the 1-2 place, and one's on the diagonal and zeros elsewhere. That's a root subgroup. So each element of the ring occurs as the 1-2 entry of one of these matrices. Okay, so you can actually embed the ring as a definable subset of the group. Is it definable? That's not obvious, but it is. Okay, we'll see why it's definable in a minute. definable group theoretically. We're not allowed to use matrices, you see, we have to define it just using group operations. The addition of the ring, well, if you multiply two such matrices, you simply add the matrix entries here. So that's certainly a defined group theoretically. Ring multiplication is not so obvious. You have to if you want to multiply the entries here, you have to form the commutator of something in the 1-3 place. Sorry, in the 1. If you form the commutator of something in the 1-2 place with something in the 1-2-3 place, you get something in the 1-3 place. Okay, that's a familiar bit of matrix algebra. And the entry in this is going to be the product of the entries there and there. But of course, we've identified the ring with E1, the 1-2 root subgroup, okay? So you then have to conjugate back inside the group to get it all into U1-2. So to sum that up, anyway, you can identify the ring with a certain root subgroup in this matrix group, and the ring addition is multiplication in the group, and the ring multiplication, you construct it by forming commutators, well, conjugating this one to that one and to that one, and then forming a commutator and then conjugating back from that one to that one. Okay, so that defines ring multiplication group theoretically. So that's what we mean by interpreting the ring in the group. Okay, now what's not so obvious is the third condition, which is that you take an element of your group gamma. Okay, it's a matrix. Each of its matrix entries you now represent by another element of gamma, namely one of these little root elements. So you get this weird map from gamma into essentially n by n matrices with entries in gamma, again, an unnatural object. And you've got to show that this map is definable group theoretically. Okay, in other words, for each pair ij, the element of U12, which corresponds to the ring element, which corresponds to the matrix entry Gij, which is a ring element, can be defined group theoretically inside gamma. So it's not obvious that one can do this. But anyway, there's a theorem. Now joint work with Katrin Tent, we sort of picked this up and carried on with it after Nies moved on. So we wrote a second paper studying Chevalley groups. We thought, well, if we could do it for SLD, we should be able to do it for. We did it for SLD over the p-adic integers. So we thought, well, let's do it for a Chevalley group over any ring and see what happens. And indeed, we got a theorem which goes like this. So G is an adjoint simple Chevalley de Mazur group scheme of rank at least 2. So SL2 is excluded. In fact, it's not true for SL2. It's true for SL2 over the p-adic integers using the other machinery that I mentioned before. But it's not true for SL2Z, for example, as everyone would guess. Anyway, because SL2Z is almost a free group. So what's the theorem say? You have an adjoint simple Chevalley de Mazur group scheme of rank at least 2 and a commutative integral domain R. Then the group of R points of G of R, is bi-interpretable with the ring R. So in other words, any first order properties of the ring are equivalent to first order properties of the group. They translate. I'll say what I mean by almost always in a minute. We believe it's probably true without it always, but there's a small gap in the proof. So, right. So to illustrate the definition, I've done that. That's where I want to go, right. Okay, so what is a Chevalley de Mazur group scheme? If you don't know too much about group schemes, don't worry. Everyone knows about Chevalley groups, the usual ones, symplectic groups, orthogonal groups, and special linear groups, and so on. Okay, so you can take because R is an integral domain, the group GR is simply G of K, the ordinary Chevalley group over the field. So G of R is simply G of K intersected with SLDR, where K is the field of fractions. And G of K is a usual Chevalley group of matrices. However, I've emphasized that it's actually a scheme because this actually does play a part in the proof. And one of the great things I've learned from working on this is, first of all, how to calculate in Chevalley groups, which I was always a bit frightened of. But once you start doing it, it's not too bad because a lot of stuff is actually there in the literature. And then towards the end, we actually needed the scheme, and that was really exciting because there's one place where thinking of it as a scheme really helps, which surprised me, but I hope I will be able to convince you that this works. Okay, almost always means there's a slight gap in the proof. If G is a group of type E6, E7, or E8, or F4, and the ring R has no units apart from the identity, then there's a small gap in our proof. Because for most cases, most rings, we don't need units, but for most groups, I mean. But in the case of these particular exceptional groups, we do need at least one unit. In particular, if the characteristic of R is not 2, then 1 and -1 are always distinct, so it always has at least 2 units. So there's no exception there. Okay. So let me talk a bit about the proof. Okay, the first step, and what takes the longest part of the paper actually, is showing that these root subgroups are definable. Do you remember in the case of SLD, I said you take elements of the form 1 plus R times E1, 2. That's what's called a root element. So in general, in Chevalley groups, they're generated over a field, they're generated by root subgroups, these elements called X alpha of R root elements. So U alpha is a particular root, is a root subgroup for any root. You take any non-trivial element of the root subgroup, look at its centralizer. Root subgroups are abelian, so the centralizer contains the whole root subgroup. And in fact, the centralizer, if you then take the center of the centralizer, you get exactly the root subgroup. That's assuming the group is adjoint, when I said as above. I'll come back later to groups which are not adjoint, in fact. And if the group is not adjoint, you then, of course, have to add a little bit more, namely the center of the group. There might be some scalar matrices. Okay, when I said usually, when we started working on this, we asked around the experts, and they said, oh, of course, that's true. It's a well-known fact that a root subgroup is its own double centralizer. But in fact, we found an exception. If you take a ring without many units, for example, the integers, or a ring like F2 polynomials over a field with 2 elements, where there are just 1 or 2 units, and G is a symplectic group, then this double centralizer is actually a little bit bigger. It's not a 1-dimensional group, it's a 2-dimensional group. So that surprised us. But it doesn't matter very much, we can get around it. The point is that using this, including the exceptional case, we can show that if you take U alpha of R, in other words, the R points of a root subgroup, then that's definable group theoretically inside the group. Because, of course, being the centralizer of an element is group theoretically definable, and to say that something commutes with something definable is again definable. So this is definable group theoretically. You see, you don't have to mention the ring or the matrices to define that. Okay, so the way these things are defined is that U alpha of R is in bijection with R. It consists of root elements. So you can interpret the ring R inside the group as a root subgroup. You just pick a root. And then we define...
Dan, sorry, can I ask, how do you define U?
So how do we do? Oh, it could be... when I say definable, it always means with parameters. You're allowed to... We pick some element and fix it.
So
it's a chosen constant from the group.
You're allowed to use constants.
Yes, we're allowed to use constants, exactly. Yeah. Yes. Without parameters, I think this probably is not true. In fact, it's certainly not true without parameters, because the point about if you have something that's bi-interpretable without parameters, then the automorphism group is the same. And it's very easy to see that the automorphism groups are not the same in general. I mean, for the ring and for the group. Okay, the group has far too many automorphisms. But if you have automorphisms which fix the parameter, then you get automorphisms of the ring. Okay, thank you, Andre. That's a good point. Okay, so we've got this definable subgroup, and addition in the ring is simply multiplication in this group subgroup, because that's how it works. These are defined as little exponentials, if you remember from your Chevalley groups. Okay, and then as we did for the special linear group, you can use the Chevalley commutator relations to define ring multiplication. First of all, you've got to identify various root subgroups by using conjugation with some element from the Weil group. If the root subgroups have the same length. If they're root subgroups for roots of different lengths, you have to use commutators as well. Anyway, you can group theoretically identify different root subgroups. Then you can use the Chevalley commutator relations to define multiplication of ring elements as corresponding to commutation between elements of these root subgroups. So that gives you the interpretation of the ring inside the group. Of course, the group can be interpreted inside the ring as matrices. That's familiar. And the difficult bit is, where we had to work quite hard, is to show that you can, the map you get from the group to this strange object, which looks like matrices whose entries are again in the group, that map is group theoretically definable. Okay, so how do you do it? Well, we know how to define it actually on a root subgroup. You've identified the ring R with a particular root subgroup, U alpha R. So an element little r corresponds to what's usually denoted as X alpha R, this little exponential of thing that you get in the Chevalley theory, which I called R dashed. Okay, so you get a map from GR back to itself, because a matrix G goes to its entry G, to its ij, sorry, G is a matrix that has entries Gij. So the elements Gij dashed are again elements of U, because Gij dashed. So you can think of this map theta maps G of R into D by D matrices with entries inside U, which are elements of G. And we need to show that this map is definable in group theoretic language without mentioning the ring. So how do you do it? Okay. Well, first of all, X beta R is expressed as a certain polynomial in R. Usually it's linear or quadratic, in fact. So in the case of SLD, it's just a linear thing. It's just R itself. I mean, it's the entries of the matrix X beta R, the example I gave you, they're either 1 or 0, or in one place it's R itself. Okay, but in the other groups you sometimes get quadratic expressions. Okay. Also, the other thing, this identification, either X beta R is conjugate to X alpha R, or you can obtain it from X alpha R by conjugating and then commuting with some other root element, X gamma of 1, say, for a certain third root gamma. Anyway, the point is that we can identify these root subgroups using group theoretic language. I already said that when I was telling you how we identify the ring, okay? And so if you've got this element, X alpha R, well, it maps to itself, obviously, okay, if alpha is actually the root we're using. And if you have a different beta, you either you map it to the corresponding X alpha either by, so I don't mean it maps to itself, I mean it maps to its ij entry, right, it maps to itself, yeah. I'll leave it as it is. So anyway, you have a group theoretic way of identifying the matrix entries of each root element x beta of R. As I say, they could be 1, they could be 0, or they could be some other root element. Okay, so if you've defined this map theta, we know theta is a group homomorphism just from the way it was set up. It's an isomorphism actually. So if you know how to define it on the elementary root elements, then you can define it on any product of n elementary root elements for any fixed n in an obvious way. So the restriction, in other words, the restriction of theta to the set I call En of R, which is products of n root elements, is group theoretically definable. Okay, sometimes, quite often, a Chevalley group will have finite elementary width. In other words, every element of the group is a product of boundedly many root elements. This is certainly true when R is a field. I mean, this should be a familiar thing to people who know Chevalley groups, because your Brouillard decomposition tells you that the group is every element of the group is a product of positive root elements times some diagonal elements, which can be written as products of root elements again, possibly times a Weil group representative, which again can be written in that way, times some negative root elements. So this is kind of a familiar thing. You get finite elementary width, it's called. So the argument I've given so far says that if your group GR has finite elementary width, then it's bi-interpretable with the ring R. I've swept aside this question of whether the group is adjoint or not, but most of what I said above doesn't depend on the group being adjoint. As I say, the definability of the root subgroup needs a little bit more work, but it still works. Okay, so what cases do we have? As I said, when R is a field, G of R has finite elementary width, Brouillard decomposition. If R is a local ring, there's a paper by Abe, which describes the structure of these groups, Chevalley groups over local rings, back in, I think, the early 1960s. And again, they have finite elementary width in this sense. And if R is a ring of integers in a number field, some famous work by Tavgen, which I think was in the early 70s. I remember when it came out. I mean, he was interested in showing that these groups, G of R, are boundedly generated product of finitely many cyclic subgroups. But what he actually proved was that they have finite elementary width. Every element is a product.
Tavgen was in 90s, not 70s.
Sorry?
Tavgen was in 90s.
In the 90s?
Yeah.
Yes, you're right, I remember.
He's of my age.
Yes, because I think it was around when I came to visit you in Minsk.
Yeah.
Wasn't it?
Yeah.
Yeah, sorry, it was the 90s. It's all muddled in my memory. So, okay, so that's when, so for a long time we had this theorem that the group and the ring are bi-interpretable when the groups have finite elementary width. And then I did a lot of very hard work of case analysis of some other cases. Many, many pages of analysis dealing with other cases. And then we found this wonderful result, which gets rid of all the case analysis. When the group is adjoint. So let me just mention how this goes. If G is adjoint, it's quite easy to see, using, for example, the result I mentioned before, that if an element commutes with all the root elements evaluated at 1, then it must be in the center of the group. So if the group is adjoint, that element is just the identity. So this means that an element of G of R is uniquely determined by how it acts by conjugation on these root elements, x beta of 1. Okay. So if we want to define your group, we've got this isomorphism theta. And I want to show that it's definable using group theoretic language, okay? It's enough to specify using group theoretic language how it acts on each, or rather, how G theta acts on X beta 1 theta. In other words, if I can identify theta on each element of that form, each conjugate of X beta 1 by G, then that tells me what theta of G is. Okay, now here's this wonderful result. Although the group might not have finite elementary width, elements of this form do have bounded elementary width, always. So this was an observation by Stepanov, and Alexei Stepanov, I think, who I think is probably one of Vavilov's group in St. Petersburg. They certainly write papers together anyway. So here's this lemma of Stepanov. There's a number n which depends only on the root system, I is a root system, such that, oops, if you take any element G of GR and you form a conjugate of a root element by the element G, then this conjugate is a product of at most n elementary root elements again. So this is Stepanov's beautiful observation. Oops. And with this observation, you see, we can deduce that once you know this, that means you can define your map theta group theoretically on any conjugate of the form X beta 1 to the G. And then because the group is adjoint, that determines what theta is on G. So theta is definable on everywhere. So that concludes the proof of the theorem that GR and R are bi-interpretable. Okay, that was such a nice lemma. I wanted to explain roughly why it's true, because it's actually, once you see how it works, it's very straightforward. Here's a sketch proof. Okay, now I said G is not just a group of matrices, it's a scheme, which means you can think of it as homomorphisms from the affine coordinate ring of G into the ring R. So A is the affine coordinate ring of G. So you could think of A as generated by the matrix entries Xij. Oh, sorry, capital A is generated by the matrix entries Xij. But depending on the group, they may be subject to some polynomial equations, because basically G is the R points of an algebraic group. Okay, so the coordinate ring is the ring generated by the matrix functions Xij, subject to some polynomial conditions. And traditionally in algebraic geometry, you'd say the generic element is the element whose coordinates are just the variables, the x's, okay? So in this language, you think of the generic element of group G as the identity map on the ring A. So it's hom AA. It's a matrix with entries Xij, if you think of it as a matrix. But if you think of it in terms of a homomorphism, you can then apply it in a nice way. So because G is a functor, so a functor acts on objects, but also on functions. So if you think of gamma as if you think of little g as an element of GR, it's a homomorphism from A to R. So it induces a homomorphism from G of A to G of R, just by composition, okay? And what does this homomorphism do to gamma? Well, if you compose a homomorphism with the identity, you get the same homomorphism. So this homomorphism I call G hat just maps gamma to G, obviously. Okay, now, there has to be a theorem somewhere. So here's the theorem. For any ring S, the elementary group generated by all the root elements is normal in G of S. So this is, of course, a theorem due to lots of people, but in the most general form, apparently it was proved by someone called Tadei. Okay, so the elementary group is a normal subgroup, the elementary for any ring S. So in particular, you apply it to our generic ring, G of A. So in particular, if you take this element gamma, the generic element in G of A, and you conjugate X beta of 1 with gamma, because X beta 1's in the elementary group, it can be written as a finite product of elementary matrices, or I should say elementary elements, they're not matrices. Okay, so x beta 1 conjugated by gamma is some finite product of elementary root elements. Okay, so then you apply gamma hat to this equation, you apply g hat to this equation, and then you get x beta 1. I've written x beta 1 r because x beta 1 in the previous line, 1 is the identity element of A, and the one we're interested in is the identity element of the ring R. So you apply g hat to this equation, and you get x beta 1 to the g is a product, again, of elementary root elements, which are mapped, the images under G, the ones we started with in the ring A. So it's a product of n of them. And that was the claim of the lemma, that every conjugate of one of these root elements by an arbitrary element G of GR is a product of n elementary root elements, where n is bounded, independent of everything. Well, apart from the functor you started with. Okay, so that's a proof of the lemma. And that's basically why our theorem is true for adjoint groups. I'll come back to whether it's true in other cases in a minute. But let's go back to the original motivation now. I said what got us thinking about this was the question of when groups are finitely axiomatizable. Okay, well, we'd like to know which rings are finitely axiomatizable. And it turns out that finitely axiomatizable commutative rings are not unusual. In fact, there's a long paper by 4 people, Aschenbrenner, Khalif, Naziazeno, and Scanlon, where they show that every finitely generated commutative ring, rings are commutative for me, is finitely axiomatizable in the class of finitely generated rings. So that's a very general and powerful statement, much more general than holds for groups, of course. So that's finitely generated rings. If you want to go back to the rings we started with, like the p-adic integers, the rings which are relevant for profinite groups, in the earlier work with Nies, we proved that if you take rings like FQT or OQT, so FQ is a finite field, square brackets, double square brackets T means power series rings. So you have power series rings over a finite field in a finite number of variables. Or what I called OQ is an unramified extension of the p-adic integers. So in particular ZP or ZPT, things like that. These are all nice profinite rings, okay? And these are all finitely axiomatizable among profinite rings. And that's not very difficult because you can see these are all defined by finitely many parameters. You just have to express these parameters ring theoretically. Okay. And then fields. Again, a locally compact field is finitely axiomatizable among the class of all locally compact rings. And again, that's not so surprising because local fields are sort of classified by a small number of parameters. And Matthias Aschenbrenner proved this for us. We asked him. Okay, so if we combine these, we get the corollary for the groups now. So let G be as above. So that means it's a Chevalley de Mazur group scheme and it's adjoint. And if R has no non-trivial units, we might have to exclude a few exceptional groups. Then if group gamma is finitely generated, then it's actually finitely axiomatizable among finitely generated groups. So that's a lot of examples answering André Nies's original question, which groups are QFA. He called them QFA if they were finitely axiomatizable among finitely generated groups. So you might say, well, I'm cheating. I haven't said that the ring is finitely generated here, but it's quite easy to see that if GR is finitely generated as a group, then R itself is finitely generated as a ring. So that drops out. Okay. If you want examples of profinite groups that are finitely axiomatizable among profinite groups, again, you get lots of them because you just take these Chevalley group schemes and apply it to one of these profinite rings. these local domains with finite residue fields. And finally, if R is a local field, then G of R is finitely axiomatizable among locally compact groups. So that's a class of groups which is quite popular nowadays, locally compact. Totally disconnected groups, for example. So if R is a local field and totally disconnected, then G of R will be one of these totally disconnected, locally compact groups. And finitely axiomatizable among all such groups. Okay, I've given a couple of references. They're both on the archive, and the second paper was recently accepted by the European MathSoc. First one is still being submitted. I've got 1 minute according to my clock, so I shall talk for 1 more minute, and then I'll ask for questions. Is that okay?
Okay.
Good. I just had a couple of additional remarks, which I wrote in case I had some time left. And as I say, I have 1 minute left according to my clock. So there we are. Okay. The first one is a remark about profinite groups. When I talk about profinite groups being isomorphic, I mean in the category of profinite groups. So the isomorphisms are supposed to be continuous. This is not something you can express in first order language, obviously. But has to be established directly, you know, using the structure of the group. So here's a different kind of example. We proved, if you look at the one-dimensional affine group, take one of these local rings, such as FPT, and form its one-dimensional affine group. So it's additive group extended by the group of units. This is finitely axiomatizable among profinite groups. So that means not only that any profinite group which satisfies that particular sentence is isomorphic to this as an abstract group, it's isomorphic to this as a continuously as a profinite group. Okay, it's topologically isomorphic. But this group is, I mentioned this example, it's interesting to me because it's not strongly complete. That means it's virtually a pro-P group, but it's not finitely generated topologically, which means it has lots of finite index subgroups which are not open, which means it has lots of homomorphisms to profinite groups which are not continuous. So this being finitely axiomatizable in profinite groups does not only hold for finitely generated profinite groups. We have other examples. So that was the one thing I wanted to mention. The other thing was an open problem. One ought to leave an open problem. Again, for profinite groups, we characterize the finitely generated pro-P groups, which are finitely axiomatizable among profinite groups. Can you do the same thing for pro-P groups which have finite rank but are pro-soluble, not necessarily nilpotent? I mention this because the analog of the Auger-Sabat theorem for abstract groups was proved by Lasserre. He characterized the virtually polycyclic groups which are finitely axiomatizable among finitely generated groups. And the characterization says that every subgroup of finite index has to satisfy that necessary condition, that its center doesn't stick out too much beyond the derived group. So a possible conjecture is that if you have a polyprocyclic pro-P group, so it's a pro-P group of finite rank which is pro-soluble, that's the same thing, then it will be finitely axiomatizable among profinite groups, if and only if it satisfies the analog of this condition. Okay, so that's an open problem. And I could say a little bit about our main theorem about bi-interpretability, to what extent we need the hypotheses, but I won't because I should leave some time for questions in case anybody would like questions. So thank you.
So let's thank the Professor Dan Segal. Switch the microphone, please. Now, a question, some comments?
I have a question. So you prove that analytic pro-P groups, they are FA, but it is not if and only if.
They're they're FA among pro-P groups, but they're FA among profinite groups. Sometimes they are and sometimes they're not in the class of profinite groups.
Yeah,
I don't have only if.
So you're right. And
Because
some other groups, pro-P groups, like the width, the finite width is sort of necessary and sufficient condition, or just sufficient? Or
sorry,
just
say that again.
this
Which
finite
condition?
width which you use for analytic pro-P groups, it is sort of necessary condition, sufficient?
Finite width.
Yes.
No, that was for algebraic groups, not for pro-P groups.
Well, you mentioned it, but so what free group
Oh,
is
I see
not?
what you mean. It's for p-adic analytic. No, certainly, because for pro-P groups we have examples like these. Suppose you take a matrix group, SL3 of FPT.
Yeah.
So it's a you could say it's analytic over a ring of characteristic P. Then group theoretically, it's very far from finite width. It has infinite rank.
Yeah, and so it is not FA.
Oh, it is FA. It is FA because
right.
it's bi-interpretable with the ring.
So and free pro-P is
You
not.
can't do it. Sorry.
Free pro-P group.
Free pro-P group, almost certainly not. But I haven't actually.
But you don't know.
I don't know.
I see.
Actually, I probably do know, but I don't know if I know. If you see what I mean. I think there are probably fairly sort of general reasons one could show why it's not FA, but you could probably do it better than I can.
I never thought about this logic.
Yes. Well, nor did I, but I find it's quite nice because if the logicians ask you a question, then it makes you ask yourself different questions about groups, which I found quite interesting. As I say, it made me get my teeth into Chevalley groups, which was quite a good experience.
Some other questions? What kind of a group? No. Could you give me an example of a group that is simple and QFA group?
That is simple.
Yes, simple and with this property, QFA.
A simple group that is QFA. So QFA means finitely axiomatizable among finitely generated groups.
Yes.
So you want a finitely generated simple group. R.
Probably not finite, no?
Well, obviously finite ones, yeah. The answer is I don't know. I don't know much about finitely generated simple groups, I'm afraid. I mean, let me think. No, you see, I'm familiar with things like these Chevalley groups, which are never finitely generated, if they're simple. I mean, if they're finitely generated, they have lots of congruence quotients, so they won't be simple. But certainly, if you take a Chevalley group over a field, over say a local field, this will be QFA among locally compact groups because we just proved it. But it'd be finitely axiomatizable. It's a simple group and it's finitely axiomatizable among locally compact groups, but of course not. But it's not finitely generated.
Okay.
So your question is a good question. And the answer is we don't know. At least I don't know.
Okay. Someone have another question?
Yes, in this example of semi-direct product, which has unique profinite structure, do you have different proof?
So do I have
different proof without logic, or is it the only
different proof? This proof Now, this affine group, I proved it by interpretation. This is true. But I have a different proof for if you take the Reith product, CP with ZP, take the Reith product of CP with C infinity and its pro P completion, that group. Okay, to generate a Matabelian group.
Okay.
Matabelian pro P group. So it's CP with ZP, the pro P version of that. Okay, that one is finitely axiomatizable among profinite groups, and I proved that directly.
No, I mean
That's a
no, I mean no. In this semi-direct product, you said it has the unique profinite structure.
oh yes, the other one isn't. Yeah, that's
In
true.
order to prove it, you use logic, but
But the unique profinite structure doesn't use logic. No, you just do that by hand.
you can do it by hand. This is
Yeah.
Okay.
Yeah, no, the logic can't tell you anything about the topology. The logic can tell you that it has a unique structure as an abstract group. You see what I mean? But the logic doesn't tell you that it has a unique topological structure. You have to just verify that.
Okay, I see.
It's an exercise for this group.
Some other question?
Professor Zapata left a question on the chat.
Okay.
He asked, he said he's in the middle of a construction site, so he will not open his microphone. But he said that you explained that going to a joint Chevalley group was because of center, conjugation, etc. But I felt you wanted to elaborate eventually about certain exceptional Lie algebras.
Sorry, could you repeat that again?
Professor Zapata asked if you wanted to elaborate about exceptional Lie algebras.
If I wanted to elaborate about them.
Yes, because you went to adjoint Chevalley groups because of center and conjugation, and what about exceptional Lie algebras?
Well, the exceptional ones can be adjoint. Well, Lie groups, you mean? Rather, yeah. They can be adjoint or simply connected, except some of them are always adjoint because they have trivial fundamental group. But whether we can do without adjoint. Well, actually, I don't know. I think it's probably true without assuming adjoint, but we can't see a way to do it. It's a very small step. There's just a little bit of, you try to define this mapping on the group and say the group has got a center of order 2. And so you know what the mapping is up to 2 possibilities, right? It's, it could be, it could be a matrix or minus that matrix, for example, but we couldn't find a group theoretic way of determining which it was. So I think that that's still a challenge if somebody was interested in it.
Some other question? No, if not, let's thank again Professor Dan Segal